Hello kids, and welcome to our understanding of dissociation and versus ionization. Just a quick, I'm just going to take a couple of minutes to differentiate between the two and when you would use each of the words or the definitions that are attached to these words. And then after this, we're going to go straight into how do we use dissociation to figure out concentration of ions. It's actually kind of fun. Okay, let's just start with a simple understanding of what dissociation is and who came up with this term. So in 1887, savant August Arrhenius proposed that when a substance dissolves in water, particles of the substance separate from each other and disperse into the solution. And he called this dissociation. This is really important. This is a really cool way of understanding how things break down. And Arrhenius, this guy's a pretty cool guy too, because he gave us some understanding of how bases differentiate themselves from acids. So non-electrolytes, remember, non-electrolytes are molecular compounds. And remember what molecular compounds are. They are nonmetal plus a nonmetal. So no molecular compounds ever conduct electricity, so they're called non-electrolytes. So he was saying that non-electrolytes disperse electrically neutral particles, therefore they don't conduct electricity. Electrolytes disperse electrically charged particles called ions, therefore they do conduct electricity. Let's look at this example here. If I have this molecular compound here and it's dissolved in water, it'll just break down into small bits of this. But they don't break down into carbon, hydrogen, and oxygen. And they definitely don't break down into their ions. Like it doesn't break down into O2 minus, okay? Or H plus, AQ. They don't do that. They just break down into smaller bits of this. Whereas electrolytes, things that are electrolytes, what they do, take a look over here, is they actually break down into their ions. So in this example here, if I have NaCl, at room temperature is solid, right? If I add it to water, it becomes NaCl aqueous. And what that looks like, when it dissolves in water, it actually dissolves into your sodium ions and your chloride ions. That is very different than molecular compounds. So the positive ions, and why that happens is because there's a charge, a positive and negative, right? They are going to be attracted to the positive and negative ends of the water. That's why your sodium here is going to be attracted, because it's a positive charge, it's going to be attracted to the negative. And the chloride has a negative charge, it's going to be attracted to the positive end of the water. So let's just take a look here. The positive ions are surrounded by the negative end of the polar water molecules, and the negative ions are surrounded by the positive end of the polar water molecule. And what you get as a result is that the ions at the edges of the ionic crystal are tugged and dislodged until each one is surrounded by water molecules and is floating around as an independent entity. So this is like your little one sort of bit of your salt. And it starts to break down until eventually this is all dissolved, and it all dissolves into your Na plus. So it dissociates, and chloride ions. And it's because of these ions that we're able to conduct electricity. And we call this breaking down into ions dissociation. Dissociation is the separation of ions that occur when an ionic compound dissolves in the water. And this is the key. There has to be an ionic compound. And recall, that's a metal plus a nonmetal. As opposed to a molecular compound, which, recall, is a nonmetal. Oops, nonmetal plus a nonmetal. Excuse that. That's supposed to be an N. So here's some dissociation equations. There are two requirements of dissociation. They need to be soluble in water, and it must be ionic, okay? And because it's ionic, we use our solubility table for this to see if it's actually soluble in water. Because if it's not soluble in water, it will not dissociate because it's not soluble in water. So what a dissociation equation shows is the separation of ions in a chemical equation. Water is not shown because it is a solvent and is not consumed or changed, okay? So when we have water here and it's a liquid, it's not aqueous, and we don't dissolve water in water, so water does not dissociate. It is shown in the aqueous states for the products. Aqueous means dissolved in water, but we definitely don't use that water itself in we don't break it down. Okay, here's an example. You need to make sure the equations are balanced. Okay, so here we go. Take a look at NaCl. We know that there are no subscripts. Notice that there's no subscripts. Why? Because it only has one charge each. This is a +1 charge and this is a -1 charge. So sodium chloride breaks down into one sodium ion and one chloride ion. Take a look at this. Here's a subscript here. This is a polyatomic ion. That does not change. It has to stay as PO4. But let's take a look at how we break this down. We say, because there are 3 potassiums, I have to say that when this dissociates, because this is an ionic compound, there's your metal plus your nonmetal, it's going to dissociate into 3 potassium ions because of this subscript. There's 3 of these guys. And there's one PO4 with a charge of -3. This is not a secret. This is found in your data booklet in your polyatomic ion chart. PO4 phosphate is PO4 3-, okay? There's only one of them because there's no subscript. If there was a subscript, it would look something like, let's say calcium, well, that's not going to, yeah, calcium phosphate. Calcium phosphate would look like this. And that would dissociate into 3 calcium ions plus 2 phosphorus ions. Okay, so that's the first thing we have to understand is the use of the coefficients from the subscripts. But let's take a look at Arrhenius's definition of acids and bases before we get into trickier stuff. So bases, a firm understanding of a base is that it's an ionic compound containing hydroxide ion that has to dissolve in, it has to be aqueous, kiddos. A base like this, for example, like sodium hydroxide, for example, is only a base when it's dissolved in water. Here's another example. Barium hydroxide, in this case here, because it's a solid, is just an ionic compound. When it is dissolved in water, so it's placed in water, right, you get that, which is then considered a base because of the presence of the OH-, right? So this is a base, for example, because it's dissolved in water. This is an ionic compound. That's a base because it's aqueous. So all bases are ionic. So all bases could dissociate into, and if they're soluble in water, and that means that all bases are electrolytes. Let's take a look at acids. Acids are molecular compounds because it's a nonmetal plus a nonmetal, okay, that contain hydrogen that yield your hydrogen ions when they dissolve in water. Anything that's an acid, we say that they ionize, okay? This is a little something for you just to kind of be clear. Notice this. It is not an acid because it's liquid, okay? It's a different type of liquid. It's not water, but it's a liquid. When I dissolve this guy in water, it becomes AQ. Then, now, this is an acid. So acids are not ionic, so they do not dissociate. They ionize. Okay? So what the heck does that mean? Arrhenius came up with the idea of ionization to explain why acids are electrolytic. They're electrolytes. They conduct electricity because they ionize. The non-electrolytic molecular compound separates into ions when dissolved in water, becoming electrolytic. So even though it's a nonmetal plus a nonmetal, right? Water, the hydrogen is not a metal. Chloride ion is not a metal. Here we have it's a gas. If it were ionic, it would be solid, right? All Ionic substances are solid at room temperature. Because this is a gas, this tells us that this is not an ionic substance, but it's still in water, in the presence of water, when it's dissolved in water, it still breaks down into its ions, but we call this ionization. We don't call it dissociation. So what is ionization? It's the reaction of neutral molecular compounds forming charged ions, and it only happens with acids. All you need to know is that acids ionize and ionic substances, including bases, dissociate. But it looks exactly the same. So don't even worry about too much. That's all you really need to remember is just the two words. What is the difference between dissociation and ionization? This is just some background info, kiddos. I'm not going to test you on it. Both produce ions. The big difference is that in dissociation, however, is a separation of ions that already exist before the dissolving in water. So with an ionic compound, this is a positively charged ion, this is a positively charged ion. When it's in water, it dissociates into the appropriate ions. But ionization involves the production of new ions, specifically hydrogen ions. So what this means is that this is not an ionic compound. It is a molecular compound with hydrogen. So this only works with acids. That's it. Okay? And then it ionizes into your H plus the whatever it is. It could be hydrochloric acid, it could be phosphoric acid, whatever, your negative ion. So let's summarize here. Molecular compounds, they're never electrolytes. They only dissolve into smaller bits of itself, okay? Ionic substances, they dissociate into individual ions. Bases are ionic substances with hydroxide ions. They dissociate into positive ions and your hydroxide ions. And acids, this is all you need to know. They ionize to form hydrogen ions, okay? So these look the same. The products of these look the same, and that's all you need to know. Just know that with acids, we call this ionization, not dissociation. So let's take a look at the concentration of ions calculations. The dissociation or ionization equations for ionic compounds or strong acids allow you to determine the molar concentration of either the ions or the compounds in solution. Okay, that sounds interesting. The ion concentration is always equal. This is what's really important. The ion concentration is always equal to the whole number multiple of the compound concentration. And another thing to know is that we use square brackets to indicate amount concentration. Amount concentration is molar concentration. So square brackets mean molar concentration, which is moles per liter. So sometimes with chem, explaining something in sentences is not really useful, so we're going to break it down into examples. So here's an example of sodium chloride. Sodium chloride, remember, breaks down into one sodium ion and one chloride ion for every one sodium chloride. So it's a 1 to 1 to 1 ratio. Okay, let's compare that to calcium chloride. Notice this right here. That's a subscript, right? So this dissociates into 1 calcium ion and 2 chloride ions because of this subscript. So now it's not a 1 to 1 to 1 ratio, it's a 1 to 1 to 2 ratio. And it's the ratio that we use to go from concentration of one substance to the concentration of another substance. So let's break it down. If calcium chloride, and remember the concentration of calcium chloride is equal to 1 mole per liter, then we know that the calcium ion, right, because we're comparing these two, is also equal to 1 mole per liter. If the concentration of the sodium chloride is 1 mole per liter, then the concentration of the chloride ion, because it's a 1 to 2 ratio, is 2 moles per liter. It's as simple as that. Because the dissociation equations show that 2 moles of chloride ions are produced for every 1 mole of calcium. So it's a 2 to 1 molar ratio. So we'll go through some examples. We're going to go through 3 examples, kiddos, and I'll show you how to break it down. So guided examples. Find the amount concentration of aluminum and sulfate ions. So we're going to find the concentration of aluminum and sulfate ions, right? and sulfate ions in a 0.30 moles per liter solution of aluminum sulfate. So here's our concentration of the solution. So let's take a look at what the heck's going on. It's a 1 to 2 to 3 ratio. Okay, so you always start with what you were given. I am given this information. Okay, so how you start these equations is you always start with the square brackets. I am looking for the concentration of aluminum because I'm looking for 2, right? I'm looking for the concentration of the aluminum ions and I'm looking for the concentration of the sulfate ions. So I'm looking for the concentration of my aluminum ions. I start with what you're given, right? Because this is the only information I go by or I have. Now I use my molar ratio. This one here is what I have, right? Which is 1. And what I'm looking for now is aluminum. So here is 2 moles of aluminum. And this was 1 mole of aluminum sulfate. So then I just use my trusty calculator to go from 0.30 moles per liter times 2 over 1, and that's going to give me the concentration of my aluminum. So now I'm looking for my sulfate ions. So I'm looking for my sulfate ions. I have my square brackets. I'm saying I'm looking for the concentration of my sulfate ions. I start with this as well. This time I have 1 mole of aluminum sulfate, but my top is the coefficient for the sulfates, so I have 3 moles of my sulfate ion. So I use my calculator, 0.30 times 3 over 1, and I get my answer, and that's for my sulfate ions. Okay, that's how you do it. So let's go to a different example. Determine the amount concentration of barium. So remember, amount concentration is just moles per liter of barium and hydroxide ions. So I'm looking for barium and hydroxide ions. This time, kiddos, I'm starting with different information. I have my grams. I have 7.34 grams of barium hydroxide, and I have a volume of 150 milliliters. So I'm going to populate my equation. I have my mass, 7.34 grams. Anytime you see grams, you always find the molar mass. Here's my molar mass of barium hydroxide, and I am also given my volume. My volume is 150 milliliters. I'm going to convert that to liters, which is 0.150 liters. So what I'm going to do is I'm going to start off with my 7.34 grams, multiply by my 171.35 grams. That's going to get me moles, right? That's going to get me moles of the Ba of my barium hydroxide. And I'm going to multiply that by 1 over the 0.150 liters to get me my concentration. If you don't want to do that, then you can just simply go C is equal to N over V, find the number of moles using my grams and my molar mass, and divide that by 0.150, and that's totally acceptable to use this formula. So now that I have my concentration, now I use that to find my concentration of my ions, keeping in mind it's a 1 to 1 to 2 ratio, okay? So to find my concentration of my barium ions, I start with this, and remember we're only rounding once at the very end. Now I'm comparing my barium hydroxide to my barium ions. It's a 1 to 1 ratio. So that's where this 1 to 1 comes from. And then so it doesn't change. It's 0.286 moles per liter. Now to find my concentration of my hydroxide, I use my concentration of my barium hydroxide. This time it's a 1 to 2 ratio because for every 1 barium hydroxide, I make 2 hydroxide, right? So this is my moles of my hydroxide ion, right? And this is 1 mole of my barium hydroxide. So I use my calculator, 0.28557 moles per liter times 2 divided by 1, and I get my concentration for my hydroxide ions. So that's not too bad. Let's think of another example, last one. What mass, so now I'm looking for a mass of magnesium bromide must be dissolved to make 1.20 liters of solution with a bromide ion concentration of 0.40 moles per liter. Okay, before we lose our minds, all we're going to do is we're going to populate our equation, right? We know that the concentration for my bromide ion is 0.40. I know that I am looking for my mass, and I know that I also have my volume, 1.20 liters, and I also have my and I am looking for my mass, and we're also going to have our molar mass. Oh, so much is going on here, and it's 184.11 grams per mole. So first thing we're going to do is we're going to find the concentration of my magnesium bromide, because I need that to then find my grams of magnesium bromide. So this time I have my concentration of my bromide ions, okay? So this time it's a 2-to-1 ratio. So these are 2 moles of my bromide ion. And here is what I'm looking for, is 1 mole of my magnesium bromide solution. Once I use my molar ratio, I get my concentration for my magnesium bromide, right? I use, now this is going to be super helpful because I have, let's see, 1.2 liters. So I'm starting with my volume. I have to get to moles to then get to grams. That makes sense, right? Because once I get to moles, I can easily get to grams using molar mass. I have 1.20 liters. Here's my concentration. And it's a conversion factor. It just happens to be that the way it is perfect, 0.2 moles per liter. My liters cancel out. And now I get moles of the magnesium bromide. In order to go from moles of magnesium bromide to get to grams of magnesium bromide, use molar mass. Make sure my moles on the bottom, they cancel out. And I'm left with 44 grams. And this is of my magnesium bromide. So those are all the ways I can give you, all the different examples I can give you for the concentration of ions. So I'm going to post some practice and the key for that. You guys have a great day.